So, good evening, everyone. Welcome back to NPTL tutorial session for the course Classics in Total Synthesis, which is taken by Professor Krishna P. Kaliyappan from IIT Bombay. Myself, Sreelekshmi S. I'm a second year PhD student and a PMRF fellow doing PhD under Professor Krishna P. Kaliyappan, Department of Chemistry, IIT Bombay. So, we are here for carrying out our eighth tutorial session. So, we will be following the same pattern as earlier for today's session as well. So let me share my screen and we will be waiting a couple of minutes to see whether anyone is joining or not. So I hope my screen is visible to you and my audio is clear as well. So we will wait for 2 more minutes and see whether someone is joining, then we will start the discussion. Okay, so let's start with today's session. So, as in the previous tutorial sessions, we will be following the same pattern today as well. First, we will discuss the week 6 assignment questions. There will be 10 questions, and we will continue our discussion with that for maybe 1 hour. And then we will discuss the week 8 lectures. We will have a discussion on the all the lectures from lecture 35 to 39 of various natural products total synthesis. We will have a brief summary of that lectures, and we will discuss the important reactions discussed in that lectures, their mechanisms. Yeah, similar to that pattern which we followed in the last tutorial sessions as well. So today is the eighth tutorial session. So let's start with the discussion of week 6 assignment. So first question is identify the major product in the following transformation. So here a reaction is given, like this particular compound is treated with this para-nitrobenzoic acid and sodium bicarbonate in chloroform. So what will be the major product in this reaction? And four options are given here. So I will give you some time to think about this, what is happening in this reaction. So I hope this is clear now what is happening in this reaction. So here, which group will be participating? So this is not the para nitrobenzoic acid. As you can see, this is the peroxy acid. So this is C double bond OOH is there. So it is a para nitro perbenzoic acid type of compound. So what it will be doing is like similar to MCPBA. MCPBA is metachloro per benzoic acid. So similar to that, it will convert this alkene into corresponding epoxide. So here, let me take the pen. So here it will become epoxide. This alkene will not be there. This will become epoxide. And in the same port, what will happen is here, this oxygen lone pair will attack either from this side, or it can attack from this side, and this epoxide ring will be opening. So what will be the major product corresponding to that? So here the correct answer will be this one, option D. So as you can see here, epoxide will be forming, and this corresponding hydroxyl group from the acid will attack this epoxide from this position, and this epoxide ring will open, and here it will come OH. So how many membered ring will be forming? 1, 2, 3, 4, 5. 5 membered ring will be forming. If it was here, it would be 1, 2, 3, 4, 5, 6. So better than 6 membered ring, the preference will be going to the 5 membered ring. That is why correct answer will be option D. And like this, it will be forming. First it will form this peroxy acid will form epoxide at this alkene, so this will be the intermediate, and intramolecularly this will go and attack this, and this epoxide ring will be open to give this product. So option D will be the correct answer. Now the next question is, what is the major product formed in the following transformation? So this given compound is treated in three sequence, first with NOCl and pyridine, then under photochemical condition, and then hydrolysis. So it is a named reaction. So what is this reaction, and what will be the major product in this transformation? So this mechanism of this type of reaction we have already discussed in the previous class as well. So it is actually Barton reaction. So what is happening first? So what is happening first is that this hydroxyl group will react with this NOCl and pyridine to form here ONO. Then the Barton reaction will take place by the delta hydrogen abstraction. So here this methyl group is having one hydrogen. So it will be one alpha, beta, gamma, delta. So from this delta position, hydrogen will be abstracted to this position. So here it will be OH and here it will become ON. I will show the mechanism. So the correct answer for this question is option D, this one. And how it is coming? This is the mechanism, general mechanism for Barton reaction followed by this photochemical condition and hydrolysis. So here under NOCl pyridine condition, this hydroxyl group is converting into ONO followed by this delta hydrogen atom abstraction will result in here O radical and NO radical under photochemical condition, and here from here H radical will be abstracted by this oxygen. So here OH will come and this carbon radical will combine with this NO radical to give this corresponding compound. Then under hydrolysis condition it will be converted into hydroxylamine, and then this elimination will result in the hydrolysis will give this corresponding aldehyde. So the correct answer will be this aldehyde, option D. So that is the mechanism of Barton reaction. First, this under NOCl pyridine condition, this here it will become ONO. Then under photochemical condition, that ON bond will cleave and O radical and NO radical will be forming. Then from here, the hydrogen atom will be abstracted by this O radical. So here it will become one carbon radical, which will combine with this NO radical to form here carbon and NO bond, which can be hydrolyzed to give the corresponding aldehyde. So this is the enolized form of this NO. That is, one proton is subtracted from here, so it will become double bond NOH. This is like the enol form, and from here it can be hydrolyzed to get this aldehyde. So that is the mechanism for this reaction. So this is the named reaction, Barton reaction. Now the next question is identify the major product in the following transformation. So this hydrazine kind of compound is treated with this aromatic compound under polyphosphoric acid. So what will be the major product? This is also a named reaction. So identify the major product in this transformation. So here I am not going into the details of the reaction. So this is a named reaction which is known as Fischer-Indol synthesis, as we all know, catalyzed by this polyphosphoric acid. So this will be resulting in the formation of this indol kind of ring, which is functionalized at the second position. So I hope it is clear. This detailed mechanism, I hope you all know, that is Fischer-Indol synthesis. So the correct answer for this question will be option D. So I can briefly explain. I have not included here, but if I am briefly explaining, it means first this ketone will form iminium ion with this NH2, and then deprotonation will take place to get the corresponding product, and then rearrangement will be taking place, and then again cyclization will happen to form this corresponding Fischer-Indol derivative. That is, Fischer-Indol synthesis is actually one of the oldest and most effective method for the development of indole, and this is one modification for that. So this aryl hydrazone will be forming, that is formed by this treatment of this aryl hydrazine and this ketone in presence of this acid catalyst. That is, here it is polyphosphoric acid. So that will first that hydrazone will be forming with this NH2 and this ketone, and that will get protonated and isomerization occur to get the enamine tautomer. Then an electrocyclic rearrangement, that is 3,3 sigma tropic rearrangement will happen, where this nitrogen nitrogen bond will be breaking, and so a double imine like this, here it will be a double NH, and here it will be C double bond NH. So the double imine then rearomatize the benzene ring to provide an anilino-imine whose nucleophilic amine group attack the imine intramolecularly to form this amino-indolin type of molecule. Then finally a loss of ammonia molecule and aromatization will give this indole. So that is the general mechanism. So this is basically the Fischer-Indol synthesis. Now the next question is, what is the major product formed in the reaction given below? So this is also a named reaction. This diol, upon treatment with this H2SO4 in H plus medium, what will be happening? What will be the major product in this reaction? So this is an example for basically one rearrangement reaction, that is pinacol-pinaclone rearrangement. So the correct answer will be option C, that is this five-membered ring rearranged to form this six-membered cyclohexenone derivative. And here the pathway is like this. So here under H2SO4 condition, this hydroxyl group will get eliminated, like it will get protonated and this water molecule get eliminated. So here one carbocation will be forming, and that carbocation, from that carbocation this bond will migrate to that carbocation, resulting in one positive charge here, which will be stabilized by the removal of this proton to form this corresponding ketone. And one possibility is the formation of this compound. Then another possibility is the option A, that is if it is getting protonated at this hydroxyl group here. If it is getting protonated, if it is getting protonated at this corresponding hydroxyl group here, then this H2O will eliminate and positive charge will be on this carbon atom, and then the sphenyl group will be migrating to form this compound. So this, as we told, this option C is our major product rather than option A. The reason is that the positive charge resulting from the elimination of this water molecule will be stabilized additionally by these two phenyl groups, where there is no such stabilization if the carbocation is forming at this position. So this will be favored rather than this intermediate. So option 1 will be the major product in this case. So this is an example of pinacol-pinaclone type of rearrangement. Now moving to the next question, that is fifth question. Identify the reagents causing the following transformation. So here, as we can see, this alkene is converted into this ester type of group, like one CH2 and then this ester. So what will be the reagents required for this transformation? So here the correct option is option C. That is first this allene, then H new condition in DCM, and then second one is MEOH, that is ozonolysis and quenching with DMS. So what is happening is here is first 2 plus 2 cycloaddition, that is photocycloaddition with this allene type of system with this alkene. So this four membered ring, this one of this double bond will be participating to form the four membered ring, and then other double bond will be remaining as this exocyclic double bond on this four membered ring. Then ozonolysis will the help in the formation of this ozonolysis of this double bond. So it will be CH2C, and here it will be C double bond O, and ME will be forming because we are using methanol in sodium bicarbonate and dimethyl sulfide. So corresponding ester will be forming. So that is the correct sequence of reaction. First, photochemical reaction, and then ozonolysis in methanol condition and quenching with sodium bicarbonate in dimethyl sulfide. Now moving to the next question, that is sixth question. Identify the reagents causing the following transformation. So this indole derivative, it is substituted at this third position to get this compound. So what will be the sequence of this transformation in the given four options? So here the correct answer is option C, that is formaldehyde and dimethylamine. Then in second step with methyl added, third reagent is sodium cyanide and fourth reagent is LAH. So we will see what is the sequence of reaction happening here. So first, as you can see, we are up to here. So with this formaldehyde and dimethylamine, a managed type of reaction is taking place. So in situ, this reagent, managed reagent will be forming, and it will get added to this here, and it will be forming CH2 and Me2, and upon methyl added addition it will get again methylated. This nitrogen will get again methylated, and we will get this CH2 NMA3 plus, that is managed reaction followed by again methyl added addition. Then on treatment with the sodium cyanide, cyanide molecule will attack here, cyanide ion will attack here, and we will get this compound. Then upon LAH reduction it will be converted into corresponding amine. So that is the correct sequence of the reaction. This managed reaction, then again methylation of this quaternary ammonium salt will be forming, then NaCN addition, Cn minus will attack nucleophilic addition, then LAH reduction to form this amine. So that is the correct sequence. Now moving to the next question. Identify the major product formed in the reaction given below. So this iodoaniline is treated with this dimethylurea kind of derivative under this formaldehyde condition heating, which is a reversible reaction as well under HCl condition. So what will be the product in this reaction? So here the correct answer is option C. So this is basically like the protection of this aniline group, this NH2 group. So it will first form this imine with this formaldehyde. As we can see, this carbon is here, formaldehyde carbon is here. Then nitrogen will be attacking in a 1,4 addition fashion. One reaction will take place to get this compound. So this is that reaction. So the cyanoaniline get protected with this dimethyl urea kind of derivative under formaldehyde condition to get this compound, and this deprotection will take place to give the starting material back at under this aqueous HCl condition. So that is the correct answer for this question. Option C. It is like a protection of this group, this amino group protection using this urea kind of derivative and formaldehyde. Now the next question is, identify the major product for in the following transformation. So this compound under treatment with this acetaldehyde in proton condition in acid condition in during heating, what will be happening? Which will be the major product in this reaction? So here also what is happening first with this acetaldehyde, this iminium ion will be forming, and on that iminium ion, this double bond will attack, and here one carbocation will be generated. To that, this bond will get migrated to form a six membered ring. So it is a kind of ring expansion kind of reaction, and the major product will be option A. This will be the major product. So here it will form one five membered ring, that is one, two, three, one, two, like one, two, three, four, five will be from this MECHO, and here this bond will be rearranged to form the six membered ring. That is one, two, three, four, five, six. Here it will be forming six membered ring, as this bond will migrate to here, and it will be like, I will try to draw it. Okay, so this bond is getting migrated to here. So as we can see, it is 1, 2, 3, 4, 5, 6, and this N, after forming this acetaldehyde iminium ion with this double bond will get attacked to here. So it will be like 1, 2, 3, 1, 2, 3, 4, 5. 5 membered ring fused with a 6 membered ring will be forming after the ring expansion rearrangement. So this is the reaction here, and here the major product will be this option A. This will be the major product. Now the next question is, identify the major product of the following reaction. This compound on treatment with TMS chloride and sodium iodide, what will be happening and which will be the major product in this reaction. So here the correct answer for this question is option B, and this is the reaction happening here. That is, this compound on treatment with this TMS chloride and sodium iodide, it will generate in situ TMS iodide, and this nitrogen lone pair will attack on this TMS group, and this iodide will get eliminated to form this intermediate. Then that eliminated iodide I minus will attack at the cyclopropane ring, and this bond will be shifted to here, and this bond will migrate to this nitrogen to stabilize this positive charge on this nitrogen to get this compound. So this is basically the opening of the cyclopropane ring by this iodide. So then what is happening, this nitrogen lone pair will attack at this position, and this iodine will be eliminated to get this 5 membered ring. So option B will be the major product in this case. So I hope it is clear. That is what is happening in this reaction. This TMS iodide mediated ring opening of the cyclopropane ring, and then again ring closing to get this rearranged product. Now the last question of week 6 assignment is this one. Identify the major product in this transformation. So this compound is treated with this aluminum chloride in benzene. What will be the major product in this reaction? So here the correct answer is option C, and this is the reaction taking place here. That is just a Friedel-Crafts cyclization. So yes, this compound on treatment with this AlCl3 and this benzene, what is happening here is this acyl group will be getting cyclized to this position to form a 5 membered ring, like 1 2 3 4 5 membered ring, and this bond will be cleaved to get this corresponding carboxylic acid here. That is a Friedel-Crafts cyclization reaction. So that was the final question for the week 6 assignment. So we will go from the first question once more. So this was the first question. Identify the major product in this transformation. So here this first epoxide forming and epoxide ring opening by this carboxylic acid to get this lactone kind of compound to get this corresponding option D as the major product. Then the next question was related to this Barton reaction, and we have seen the mechanism of this Barton reaction, how this is converting into corresponding aldehyde. This methyl group is converting into aldehyde. That is the final reaction. Then we have seen the Fischer-Indol synthesis to get this indol derivative, and then this pinacol-pinaclone rearrangement and its corresponding mechanism, and why this migratory aptitude is preferred over this one. Then this sequence of reaction, first epoxy, this cycloaddition, and then sonolysis to give the corresponding compound. Then we have seen this reaction where managed kind of reaction followed by the quaternary ammonium salt and substitution and LAH reduction giving the desired compound. Then we have seen the protection of this cyanoaniline using this dimethyl urea kind of derivative, and then this rearrangement reaction to get this 6,5 fused ring, and then this kind of ring opening of the cyclopropane by in situ generated TMS iodide using TMS chloride and sodium iodide. And then finally we have seen this Friedel-Crafts cyclization reaction to get this option C as a major product. Now we will move to the discussion on week 8 contents, that is lecture number 35 to 39. So, in the previous lecture, that is lecture 34, we have seen the total synthesis of morphine by Gates and Obermann's group. So, in this lecture 35, we have seen the discussion on the total synthesis of morphine by Parker's group and White's group, where the discussion is basically about the application of tandem cyclization of an ortho-allyloxy aryl radical, Mitsunobu reaction, Beckmann rearrangement, carbenoid CH insertion in the total synthesis of morphine by Parker and White. So, in first Parker's approach, which was completed in 1992, it is towards the cyclization of the morphine ring system based on a tandem cyclization of an ortho-allyloxy aryl radical. And the Sparkers group reported a short 11 steps convergent and stereospecific synthesis of plus or minus dihydroisocodeine, which on oxidation completes the formal total synthesis of morphine. And the starting material used are isovanilline and phenethylamine. And one of the key reaction is Mitsunobu reaction, and he could complete this total synthesis in 11 steps with 11.63 percentage of overall yield. And in White's total synthesis, which was completed in 1997, the focus of synthetic work was unnatural enantiomer, that is plus morphine, where we have seen that carbenoid CH insertion is the key step, and other reactions like stop condensation, Robinson annihilation, and Beckmann rearrangement is also utilized for completing the total synthesis. Starting with the commercially available and cheap starting material, that is isovanilline, and he took almost 28 steps to complete this total synthesis with 3 percentage of overall yield. So that was about the total synthesis of morphine. Then the next lecture was about two natural products, that is methyl homosecodaphniphyllate and secodaphniphyllate, where we have seen the applications of sequential 1,4 addition of enolate derived from an amide to an alpha beta unsaturated ester followed by quenching with alkyl iodide as one of the key reactions to get the precursor in the total synthesis of methyl homo secodaphniphyllate and secodaphniphyllane by head coke. So these both methyl homo secodaphniphyllate and secodaphniphyllane are squalene derived natural products, and this methyl homosecodaphniphyllate is isolated from the bark and leaves of Usuriha, which is used in the treatment of asthma. And the structure of this compound, which is given here, was this one. This one was confirmed by 1971 by Sasaki and Hirata group, and it is having a highly congested pentacyclic skeleton 1, 2, 3, 4, 5, and 8 stereogenic center which are contiguous, and out of which 2 are contiguous quaternary centers. So these are the main synthetic challenges also: highly congested pentacyclic skeleton, 8 stereogenic centers which are contiguous, and out of which 2 contiguous stereo centers are quaternary centers. So Heathcock's total synthesis involves both racemic and asymmetric total synthesis, where he have used intramolecular Diels-Alder reaction and Asap-Prince reaction as the key steps. And what is the difference between this methyl homosecodaphniphyllate and secodaphniphyllane is an additional bicyclic group is present in secodaphniphyllane, and that synthesis had completed in from starting from propanol, and the key reactions were Cannizzaro reaction and Sipper reaction. Sipper reaction is basically the isomerization of internal alkynes to terminal alkynes. That mechanism we will see in a few minutes. So that was the discussion on the lecture 36, methyl homo secodaphniphyllate and secodaphniphyllane. Now the next lecture, lecture 37, was about lysergic acid. That is basically the application of Friedel-Crafts acylation and aldol condensation and intramolecular imino-Diels-Alder reaction, the total synthesis of lysergic acid by Woodward and Oppolzer. So this lysergic acid belongs to ergot alkaloids, which are the first used drugs for the treatment of migraine. And the tetracyclic core for the structure with this indole as their core is responsible, believed to be responsible for the biological activity. So we have heard about LSD, which is a derivative of lysergic acid, which is the most potent psychoactive agents, which was discovered with the psychoactive effects in 1943 by scientists from Sandoz, and it was first synthesized in 1938 by Albert Hofmann during purification in the final step when he was interrupted by some unusual sensation. And the first total synthesis of this lysergic acid was reported by Woodward's group in 1956, starting from indole 3 propionic acid. And the key step for the synthesis were Friedel-Crafts acylation and aldol condensation. And he took almost 15 linear steps to complete the synthesis with 0.78% of overall yield. And the another synthesis was Oppolzer's total synthesis, which he completed in 1981, starting from 4-hydroxymethyl 1-tosylindole. And the key reactions were intramolecular imino-Diels-Alder reaction, and he completed the total synthesis in 9 steps with 3.88% of overall yield. The next molecule was galantamine, where we have seen the application of oxidative phenol coupling, crystallization induced chiral conversion, palladium catalyzed asymmetric allylic alkylation, intramolecular Heck reaction in the total synthesis of galantamine by Barton, Dis, and Tross group. So galantamine is more or less structurally similar to morphine, and the parent member of galantamine type Amaryllidaceae alkaloids, which are isolated from Galanthus voronovi. It is used in the treatment of Alzheimer's disease due to its selective acetylcholinesterase inhibition. And first photosynthesis was by Barton and Kirby's group in 1960, where we have seen that the oxidative phenolic coupling was the key step to connect the aromatic rings in a biomimetic way. And the starting material used were isovanillin and parahydroxyphenyl acetic acid. And Barton's group could complete the synthesis in 7 steps with 0.53 percentage of overall yield. And then Jordan's total synthesis was a multi-kilogram scale synthesis which was completed in 1999 starting from dimethoxybenzaldehyde, and the key steps were oxidative phenolic coupling, crystallization induced chiral conversion of plus or minus narvadine to minus narvadine, and he could complete this total synthesis in 9 steps with 12.4 percentage of overall yield. And this is a practical and cost effective synthesis to pilot plan scale up for clinical trials. Then the next total synthesis which we see for this galantamine was Strauss total synthesis, which was completed in 2000. And the key steps were palladium catalyzed asymmetric allylic alkylation and intramolecular Heck reaction. This was the first total synthesis where oxidative phenolic coupling was not used, and the starting material used was isovanillin. And he took almost 17 steps to complete this total synthesis with an overall yield of 1.13 percentage. And the final lecture, lecture 39 of the week 8 lecture series, was the total synthesis of epibacterin, where we saw the application of reductive palladium catalyzed Heck type coupling, microbial oxidation, palladium catalyzed desymmetrization of cis 3,6 benzyloxy 2 cyclohexene, and a palladium catalyzed cross coupling, fluoride promoted fragmentation, and Hoffman rearrangement in the total synthesis of epibacterin. And we have seen Regan's total synthesis, Olivo's total synthesis, Lay's total synthesis, Tross synthesis, and Kibayashi's asymmetric total synthesis. So this epibacterin is isolated from Eucharodoran poison frog Epipedobacter tricolor, and it contains chloropyridine, and it appears to be unique in possessing the 7-asa bicyclo 221 heptane ring system, and its analgesic activity is about 1 by 200 dose of morphine. And the we have seen first the Regan's total synthesis, which was completed in 1993, which was a racemic synthesis and a concise, highly convergent and complete stereoselective for the desired XY isomer, where the key step were reductive palladium catalyzed Heck type coupling, and the starting material used was pyrrole and 2-aminopyridine. And he could complete the total synthesis in 2 steps with 25.9 percentage of overall yield. Then in Olivo's total synthesis, which was completed in 1999, he followed a biocatalytic approach starting from hydroxycycloaminohexene hexene, and the key steps were intramolecular nucleophilic displacement of the starting material, microbial oxidation of unfunctionalized carbon, and coupling of chloropyridyl ring to 7-azanorbornane with an overall yield of 8.11 percentage. Then in Lay's total synthesis, which was also completed in 1999, using 10 steps using an organized array of polymer supported reagents and sequestering agents in a successive manner. No chromatographic purifications are required to afford the product in greater than 90% purity in 10 steps. And the starting material used were 6-chloronicotinoyl chloride, and key reaction, another key reaction was intermolecular Diels-Alder reaction, where he could complete the total synthesis with 32.5% yield for plus or minus exoepibacterium in 10 steps. And then in Trost total synthesis, which was the first asymmetric total synthesis completed in 1996, the key step were palladium catalyzed desymmetrization of cis 36 dibenzyloxy 2 cyclohexene and a palladium catalyzed cross coupling. The starting material used were cyclohexadiene, and he could synthesize this compound in 10 steps with 13.36% of overall yield. Then in Kibayashi's asymmetric synthesis, which was completed in 1998, the key step was asymmetric heterodyl-Salder reaction, and he could complete the total synthesis in 9 steps with 3.6% of overall yield. So that was the 5 lectures of the last week. Morphine, methyl homosecodafniphyllate and secodafniphyllite, lysergic acid, galantamine, and epibacterium. So I'll give you some time to go through these lectures once again, these main points what I have discussed today, and then we will go to move towards our discussion on some of the key reactions that we told today, that we mentioned today. So I hope it is clear. Now we will move to our discussion on the key reactions that we discussed today. So first was Mitsunobu reaction. Previously also we have discussed about the mechanism of this Mitsunobu reaction. So it is basically the conversion of stereochemistry at this. It is a nucleophilic substitution, but in an essential manner, that is stereochemistry of this alcohol will be changed in the substituted product, and the reagents used are pph3 and diethyl azo-dicarboxylate. So the mechanism of this reaction is like this. First, this pph3 will get coordinated with this nitrogen, and here it will be O minus, this diethyl azo-dicarboxylate. Then this nitrogen will abstract this proton from this nucleophile, generating this free nucleophile, and this compound will be forming. Then our alcohol will take up this pph3 due to its affinity towards phosphorus, and we will get this byproduct. And then again this nitrogen will take this proton from this alcohol compound, and we will get this as the major byproduct, that is diethyl 1,2 hydrazine dicarboxylate. Then in the next step, this oxygen binded with pph3, due to its strong affinity of this oxygen with the pph3, it will eliminate as a stable triphenyl phosphine oxide, and we will get the substituted product by the attack of this nucleophile. So as we can see, the nucleophile will be attacking on this carbon in an SN2 manner. That is, it will be attacking from the opposite face of this oxygen. So in the resulting nucleophile added product, we will be getting the opposite stereochemistry as that of the alcohol. So this is the mechanism for this Mitsunobu reaction, that is conversion of this alcohol into this nucleophile substituted product by using this triphenyl phosphine and diethyl azo-dicarboxylate. Now the next reaction is stop condensation reaction. That is basically the reaction of aldehyde or ketone with this dialkyl succinate in the presence of this base and further acidification to get this alkylidine succinic acid monoalkyl ester. So the mechanism for this reaction is first the base will abstract this proton from this dialkyl succinate, and enolate will be forming that will attack in a 1-2 fashion on this aldehyde or ketone to get this beta alkyoxy ester following this aldol reaction. Then an intramolecular acyl substitution is taking place, that is this O minus will attack this carbonyl carbon and resulting in the elimination of this OR3 group to form this gamma lactone kind of derivative. Then again this ring will open to form this compound which on protonation will result in this alkylidine succinic acid monoalkyl ester. So that is the mechanism for this stop condensation reaction. Now the next reaction is Beckmann rearrangement. This also we have discussed previously, that is rearrangement of this ketoxime into corresponding amide which is catalyzed by acid. This is known as Beckmann rearrangement, and the mechanism of this reaction is like this. That is, first this oxime will get protonated and then elimination of this water molecule will be followed by the migration of this R1 to this nitrogen. So this carbocation will be formed at this carbon center, and then the eliminated water molecule will get attacked on this carbon center and deprotonation will give this intermediate, which on tautomerization we can rearrange it into amide. So that is the mechanism of Beckmann rearrangement. Oxime is rearranging into corresponding amide. Now the next reaction is Robinson annihilation. This also I am not going into details because we have already discussed this. That is the basic mechanism is this enolate formation and then mycladation and followed by aldol condensation. That is deprotonation of the ketone by sodium hydroxide resulting in this enolate. Then conjugate addition, that is mycladation, and then aldol reaction will take place. Aldol condensation will take place to form this diketone type of compound, this mycladect, and then the cyclization will take place to give this Robinson unrelated ring product. Now the next step, next reaction is Asa-Prince reaction. So that is basically the acid catalyzed addition of aldehydes to alkenes, and it will give different product depending on the reaction condition. So in the case of Asa-Prince reaction, we will be using this nitrogen analog, and it is this kind of nucleus is present in alkaloids like piperidines, indolizidines, quinolizidines, huperzine, lyconidines, cylindrosines, and cortistatin. So the mechanism of this reaction is this Bronsted acid or Lewis acid catalyze this kind of imine type of formation with this ketone and this amine, and that will be cyclized to give this compound which is quenched. This carbocation will be quenched by the nucleophile to give this corresponding product. So this imine formation then followed by cyclization. So this bond will like a 3 3 sigma tropic rearrangement will take place. In type of reaction will take place and the cyclization will happen where the positive charge will be quenched by this nucleophile. That is basically Asa-Prince reaction. Now the next reaction is alkyne zipper reaction. Before that you may go through this Asa-Prince reaction for some time. Now the next reaction is alkyne zipper reaction, which is catalyzed by this kappa that is made from this lithium 3-aminopropylamide or this 3-aminopropylamine in general, which on treatment with this butyl lithium will give lithium 3-aminopropylamide, which on treatment with this potassium hydride will give potassium 3-aminopropylamide, which will catalyze this reaction. So this internal alkyne, this proton will be abstracted by this kappa, and this will get added to this will take this proton to get this allene derivative. Then again the same thing will be happening. The next proton will be taken by this, and this will be attacking on this alkene will take this hydrogen from here, then again allene, and then again it will convert it into terminal alkyne, and then this proton finally will be taken up by the this base, that is kappa, and which is hydrolyzed to get this terminal alkyne. So this is basically the isomerization of term internal alkyne to terminal alkyne, and this process will continue until the alkyne will reaches the terminal position and there is no further proton to abstract in the terminal position. So that is alkyne zipper reaction. Now, the next reaction is Cannizzaro reaction, which is the reaction of this formaldehyde, that is ketone or aldehyde without alpha hydrogen atom in presence of NaOH giving sodium formate and methanol. So this is basically the reaction. This OH minus from this base will attack at this carbonyl carbon to form this, and that proton will be taken by this next molecule of that same compound, and that will result in the formation of this compound. Then again that reaction will continue to form this methanol, and hydrolysis of this compound will give resulting in the formic acid. So this is the mechanism for Cannizzaro reaction. And next reaction is Friedel-Crafts acylation. And these all are the basic reaction. That's why I am not going into the details of this reaction. So here this acylating agent, that is acetyl chloride, we are using in presence of an aromatic compound and Lewis acid catalyst. This acyl group get added to this aromatic compound by means of this Friedel-Crafts acylation. And the byproduct here is hydrochloric acid. So the mechanism is as given here. This AlCl3 will coordinate with this chlorine, and that will get eliminated to get this acylium anion with acylium carbocation, which will get attacked to this aromatic ring, and then it will rearomatize to form this aryl ketone. So that is the mechanism for this reaction. So that were the basic reactions which were included in the week 8 lectures, that is Mitsunobu reaction, Stokes condensation reaction, Beckmann rearrangement, Robinson annulation, Asa-Prince reaction, alkyne zipper reaction, Cannizzaro reaction, and Friedel-Crafts acylation. So I hope this is clear. So that's what is about the content for today's session. I hope it is clear. Thank you for listening. If you have any queries, you may post in the NPTL Swayam portal. Thank you for joining. Thank you.